All right, well, welcome to Unit 3, all about energy and momentum. And we're going to start by talking about momentum and a related concept of impulse. So we might as well start with a definition. If we have a particle here, mass m, traveling with some velocity vector v, we can actually define a momentum vector, which is just equal to mass times that velocity vector. So momentum is a vector, and because it's just a scalar times velocity, that momentum vector is always going to be parallel to our velocity vector. There's our momentum vector p. It's worth asking ourselves whenever we get a new quantity what we can do with it. And one of the things we always want to start with is what are our units? Well, if you look at our units here, we end up, that's not great. We end up with units of, well, mass is in kilograms. Velocity is in meters per second. So we end up with units of kilogram meters per second. Now, there's an equivalent unit here, which is, if you might remember that a Newton is a kilogram meter per second squared, F equals ma. This is also equal to a Newton times a second, or a Newton second. So these are both equivalent units that we will use. If we have just one particle like this, one thing kind of jumps out at us right away, that if we look at force, right? We just finished up a unit on force. If I apply a net force to that particle, what do I get? Well, it's ma. I know F equals ma. But I can also write, because of kinematics, as this is m dv dt. And in the case where mass is constant, what we can do is we can write this actually as the derivative of momentum. And this is actually a really important little concept here, that forces, what do forces do? Forces change momentum over time. If you apply a force for a certain amount of time, it changes your momentum. And in fact, if you were Isaac Newton, which you're not because he's dead, but if you were Isaac Newton, F equals dp dt is exactly how you would have done this. Why P stands for momentum, by the way, I don't know. There's no P in it. Ask somebody else. So we're going to start by working just with this real quick. And I want to note one thing. What if your net force is 0? Well, we already know from our last unit that if the net force is 0, that means our velocity is constant, or we're in equilibrium. But notice this also means that dp dt, the derivative of our momentum is constant. The derivative of our momentum is 0, which tells us, among other things, that our momentum is constant. A good thing to know. All right, what if we try something a little bit strange here? What I'm going to do is I'm going to take an integral of both sides. So I'm going to take this f equals dp dt. And I'm going to integrate both sides over time. So I'm going to take an integral from some time 1 to some time 2 over some time interval t1 to t2. That is, I'm going to apply a force to this object. So maybe I've got, a box or whatever sitting here. And I'm going to apply a force to it for a certain time, delta t, between t1 and t2. Well, on the right side, notice I'm taking an integral of a derivative, and for those of you who are taking calculus, integrals and derivatives are opposites of each other. So what I actually get here is I get my momentum at time 2 minus my momentum at time 1. And we're just going to write this as the change in our momentum. So the right side just turns out to be the change in my momentum. The left side, this integral of force over time, is actually a special quantity that we are going to call, this whole thing over here is a special quantity we are going to call impulse. We have a special letter for it. It's actually J. Sometimes you'll see it as I, but we're going to use J in this class. We get J. J equals delta P. So that integral of force over time we call impulse, and it's just the change in our momentum. So if I have some force that's constantly changing, I can integrate it to figure out what its effect on momentum is. So in general, right, let's say I've got some complicated force, right, because usually in the real world, forces aren't nice and constant. Let's say I have some complicated force, right, that changes over time when I'm applying it to this object. Well, if I can find the integral, if I can find the area under that curve, that's going to be equal to my impulse, which is going to be equal to the change in momentum of my object. And it could be positive, it could be negative, depending on whether my force is positive or negative. One thing that's worth always asking is what happens if our force is in fact constant? If our force is in fact constant, then our graph would look instead like this. We've got some constant force, or if we're just interested in the average force over some time interval. Well, in this case, my integral becomes rather easy. It's just the area of that rectangle, and I happen to know that the area of that rectangle would be my average force times delta t, which is whatever my elapsed time is. And that's going to be equal to the change in my momentum. So this is what happens to impulse if F is constant. This is, by the way, something we'll see an awful lot. Notice if my force is constant, instead of an integral, instead of the integral of F dt, when force is constant, it just becomes multiplication, it just becomes F times t. So that's something you see a lot, that when things are constant, integrals become multiplication, derivatives just become division. This actually you'll often see written in a special way for physics classes, which is if you assume that mass is constant again, you get F average delta t equals m delta v. And this is sometimes referred to as the momentum impulse formula. Well, it's actually, this is the momentum impulse formula, but we will often refer to this in class, if you kind of read the deltas as A's, as fat equals mav. Fat equals mav. Obviously, those aren't A's, those are really deltas. But this is a very handy way to figure out if you apply a force for a certain time, what happens to the momentum of the object. So let's consider something else in just a moment. We're going to now shift gears from considering just one object and forces on it to now considering what happens if we have two or more objects that are interacting. So take it away, Mr. Bates. Thanks, Mr. Bates. All right, so now we want to consider what happens if we have two or more interacting objects. Momentum is often used whenever you have a collision. So if you ever are looking at a problem and two things are colliding, momentum is probably the lens you want to use to look at it. So here I imagine I've got M1 and M2, and M1's sliding along some surface at an initial velocity, and it collides with M2. And then a bunch of stuff happens. And a bunch of things could happen. M1 could bounce off, M1 could stop and knock M2. In this case, we're just going to assume that M1 and M2 stick together, kind of like pieces of putty or something, and keep moving together. And let's ask, what happens in the middle of this collision to help relate before to after? Well, as you might imagine, when M1 runs into M2, it's going to apply a force to M2. We could call this force F1 on 2. It's going to apply a force to M2. And what is that force going to do? Well, as we just learned, that is going to change the momentum of block 2. So you can imagine that F12 is going to cause the momentum of block 2 to increase. Previously, the momentum of block 2 was nothing. It wasn't moving. But now it's going to get pushed on by block 1, so you might imagine that its momentum is going to increase. But remember, you've also got this equal and opposite force from M2 back on M1 that's going to slow M1 down, F2 on 1. And what's F2 on 1 going to do? It's going to cause the momentum of block 1 to decrease. And we know this, of course, because we've got our idea of impulse, right? That force is over time, whether it's an integral of force or some constant force times time, results in changes in momentum. So one thing to note here is that these forces, these internal forces, are going to cause block 2's momentum to increase and block 1's momentum to decrease. But we know something really important about these. We know that F12 and F21 are equal and opposite. So what that tells us is that whatever momentum P2, whatever momentum block 2 gains is going to be canceled out. It's going to be exactly equal and opposite to the momentum change of block 1. That is, if block 2 gains some momentum, block 1 loses the same amount of momentum. Momentum is traded between the two blocks, but any amount of momentum that block 2 gains is lost by block 1. And this is actually a really important law that we're going to talk a lot about, which is called the law of conservation of momentum. Conservation of momentum. And what the law of conservation of momentum states is that if there's no external forces, we'll talk about what those are in a second. If there's no external forces, then the total momentum of a system is constant. The total momentum of a system is constant. So whatever our momentum is before some collision or some interaction is exactly equal to our momentum after the collision. So we're going to do an example of this in just a moment, but it's worth asking ourselves, what do I mean by external forces? So in this case, there's two main kinds of forces that can occur in a system. You can have internal forces. And an example of an internal force here would be F12 and F21. F21. And internal forces are ones where our agents, right? Remember those agents? The agents are in the system, as in they should be visible within our drawing. So in this case, block 1 and block 2 are both in our drawing. They're both inside our system. Any forces between those are considered internal forces. Well, the opposite of an internal force, as you might imagine, is an external force. An external force is one where our agent is outside the system. And in this case, a good example of that would be gravity, that we've got gravity in the y direction from outside the system. We have not drawn the whole Earth in our system. So in this case, though, there is no net external force because gravity is going to be canceled out by the normal force. So in this case, all we've got are those internal forces. So we're going to say that momentum is conserved. Momentum is conserved. Whenever we're using conservation of momentum, we're going to be doing so a lot. It's often used anytime any two things collide because they're going to kind of trade off some momentum between them. You do have a couple types of collisions. There's two main types. I said in class there's three main types, and I'll clarify what I mean by that of collisions. Sorry, small glitch. So again, we were talking about the types of collisions. We have elastic, where things bounce off each other. Inelastic, where the things stick together and smush together after the collision. And some people think of an explosion where something starts together and then splits apart. Momentum is also conserved in that case. It is the case you can think of inelastic and explosions as kind of similar types of collisions. So let's do an example here of an elastic collision. So I've got a 2 kilogram block that's sliding along at an initial velocity of 1 meter per second. There we go, 1 meter per second. When it collides with a 3 kilogram block initially at rest. We find after this collision that the 3 kilogram block is moving at 0.8 meters per second. So the question is, what is the final velocity of the 2 kilogram block? So again, let's set up our initial and final momenta. So our initial momentum here is all in the 2 kilogram block because the 3 kilogram block's not moving. So I'll go ahead and get 2 kilograms times 1 meter per second for a total momentum at the start of 2 kilogram meters per second, or 2 Newton seconds if you like. Okay. At the end, we know that for our final momentum here down at the bottom, we know we have 3 kilograms times 0.8 meters per second. And we don't know what's happening with the 2 kilogram block. So we'll just write plus 2 kilograms times VF. So I'm going to write this as, 3 times 0.8, this is 2.4 plus 2 VF. Now, something very important has to be true about these two momenta. They have to be exactly equal to each other. They have to be exactly equal to each other. Because if they're not exactly equal to each other, momentum is not conserved. And as we know, momentum is conserved because all of the forces here are those internal forces between the two objects. Any momentum gained by the 3 kilogram mass is lost by the 2 kilogram mass. So we can set them equal to each other, and I'm going to do that down here. So I'm going to get 2 equals 2.4 plus 2 VF. I can do that subtraction, so I get 2 VF equals negative 0.4. And that tells me that my final velocity, if I divide by 2, is negative 0.2 meters per second. And what I love about conservation of momentum is we didn't have any idea what was going on with the 2 kilogram block, but not only have we found its final speed, we've also found that it's got a negative velocity, that it has to be moving this way. So the 2 kilogram block actually bounced off the 3 kilogram block and moved the 3 kilogram block to the right. And it's worth just noting here, remember the changes in momentum should be the same. So the change in momentum for the 3 kilogram block, well, it started out at nothing, was positive 2.4. For the 2 kilogram block, final minus initial, okay, so it ended at negative 2 times 0.2, negative 0.4, minus its initial, which was 2. So it had a change in momentum of negative 2.4 kilograms. So you can see here again just that really important notion that the changes in momenta for the two objects are, just like forces, are also equal and opposite.